Welcome to office hours. What can I do for you?
Hi, I need help with number six.
Okay, do you want to read it to me? Is this from the special homework number 10?
Yes.
Okay. All right, can you read it to me?
Fine. So let me read the universal set.
Is this the one where you have to find some sets A, B, and C that satisfy a bunch of properties?
Yes.
Okay, so the universe is 1 through 12, right?
One, two, three, four, five, six, seven, eight, nine, 10. Yeah, nothing repeating, no repeating numbers in the set.
Well, it wouldn't matter if there were.
Yeah.
Okay, so what are the properties? What are there, three or four properties that
Um
your sets need to be to satisfy, right?
A and B are disjoint sets.
All right, so that's property one. A and B are disjoint sets. What's the next property?
B is a proper subset of C.
Okay, so you need to know the definitions of proper subset and disjoint.
And you know what disjoint is. And A intersects C has at least one element.
Okay, so they're not going to be disjoint.
A times B has 12 elements.
Okay, so you need to understand the cross product.
Hmm.
So this is just a test of your understanding of definitions, really. So let's review the definitions. All
Okay.
right, because that will help you. It's just a little puzzle that you have to figure out. But you certainly know that just by definition of universal set, right?
Yeah.
Uh, Sets A, B, and C must be subsets of the universe. You understand that, right?
Yes.
And you understand what a subset is, right?
Um, yes.
Okay, let's just review. X is a subset of Y, right? X is a subset of Y, right?
Meaning all the elements in X has to be in Y.
Yep, good. All of the elements in X must be in Y, but to really get it technically, it's if X is an element of set X, then that implies set element little x is an element of set Y. So if element
Yeah.
little x is in set X, then element little x is in Y. And the reason we want to understand that is because this definition makes the empty set always a subset of any set. Notice
Yeah.
the empty set is a subset of Y by false hypothesis because if X is equal to the empty set, this hypothesis that there's an element in the empty set is a false hypothesis because the empty set has no elements. And we know
Yeah.
an if then is true by false hypothesis. So isn't that interesting? That's the reason we know that the empty set is a subset of any set because it
Hold on.
always satisfies that definition, right?
Oh, okay. Oh, you know what? I was thinking of the if P then Q. I was saying P and not Q would apply to this.
Um, It's not that the negation is true.
Oh, okay.
You're right that P and not Q would be the negation. that would mean that X is not a subset of Y. If there's an element little x in set big X and little x is not an element of set Y, yeah, that would mean X is not a subset of Y. Okay.
Okay.
But false hypothesis just means that this if then, this if P then Q has a false P, and that makes the if then true. Remember? If the hypothesis is false, the if then is always true.
Oh, okay.
Uh-huh. Now let's review just, you said you know what disjoint means, okay? So A and B are disjoint if what?
Um, disjoint if A is, I would say, not a subset of B.
For sure, it's not going to be a subset of B, but there's a little more to it, but that's sure part of it. A is not a subset of B, B isn't a subset of A, and even more, A intersect B is actually empty. They have nothing in common.
Oh, okay.
Does that make sense?
Hmm.
Okay, and now let's review our definition of a proper subset. Okay, A is a proper subset of B. Maybe I'll use X and Y. Oh, what am I doing? I meant to skip a line. Okay, so let me use X and Y. X is a proper subset of Y. It's a two-part definition. It is in
Okay.
the notes, but I'll tell it to you. Since you took the time to come in here, I'll help you with that.
Okay.
If two things. One, X is a subset of Y. And there exists some element, say little y, in set Y such that that same element, little y, is not in X. Let's draw a picture. Let's do a Venn diagram so we can really see what this means. It means here's a universe, here's Y. Okay, we'll make it big enough that we can fit
Okay.
X inside. So here's set X. Everything that's in X, all the elements in X are in Y because the whole circle of X is in Y. But
Hmm.
there's at least one element, we'll call it little y, that's in set big Y, but strictly outside of the set X.
Okay.
In some sense, it's like the strict less than. In some sense, X is strictly less than Y. You know the difference between less than or equal to and strictly less than? It's kind of the same with proper subset. You know, X is a subset of Y, includes the possibility that X is equal to Y. But if X is a proper subset of Y, X can't be equal to Y. In some sense, X is strictly smaller than Y because there's some element outside of X that is in set Y. Does that make sense?
So meaning all the elements X is equal to all the elements Y. All and if it's a proper subs oh yeah, yeah. If it's a proper subset, X all the elements X equals to all the elements Y, but not vice versa.
Exactly.
Okay.
I like that. I'm going to write that down. X is a subset of Y, but Y is not a subset of X. This is the not a
Okay.
subset of symbol. Nicely said.
Thank you.
Hmm. So do you understand what it means for A intersect C to have at least one element? Do you understand the intersection?
A Yeah, yeah. A intersects C, meaning but A and B are disjoint sets. B
That
is
means they have
proper.
nothing in common. They have no elements in common.
But
But
we
A
don't know.
intersects C has at least one element.
So technically, um A and B
Shall
would
we draw a picture?
yeah, but I'm thinking there could be like multiple. I don't know if there
Oh,
be
there are
like
lots of answers, lots of possible answers. That's what makes it fun.
okay, so I get to be creative but follow the scope of the problem.
Precisely.
Yeah.
Precisely. And, a picture can help.
Yeah.
You
A Venn
know,
diagram.
yeah, you can draw, like just to try to kind of sort it out, right?
Yeah.
Like A and B are disjoint. That
Yeah.
means A, if we draw A here and B here, they don't have any cat's eye, they don't intersect at all.
Okay.
And B is a proper subset of C. Well, B is a subset of C, but B is going to be a proper subset of C. That means C is going to have at least one element, let's call it W, that's not in B. A intersects C has at least one element. So where would we put the element that's in A intersects C? I
Probably
can
the middle of A and C.
exactly. So maybe we'll call this element, I don't know.
Let's do D.
I like it. Little d. And here's our universe. And now A cross B has 12 elements. So that puts restrictions on the size of A and the size of B, right? Because if we're going to have
Mhm.
12 ordered pairs, there's only so many ways that you can multiply the size of A times the size of B and get 12. But there are different ways to do it. See, because the size of A cross B, remember the number of ordered pairs? Well, the first coordinate comes from A, so however many elements are in A tells us how many possible first coordinates we can have. The size of B tells us how many possible second coordinates we can have. And the number of first coordinates times the number of second coordinates tells us how many elements there are in the cross product. It tells us how many possible ordered pairs there are.
Okay, so the last property has to be the format of the set, right?
Yeah, I mean, yeah, we're going to be looking at the actual elements because eventually your answer is going to be, something like, you know, let A equal something, let B equal something, let C equal something, and then you'll verify each property. You'll verify that that A intersect B is what it needs to be for them to be disjoint, right? And then you'll verify that B is a proper subset of C because, oh, and then you'll tell me, well, because you got to, verify the two parts of the definition. That A is X, well, it'll be A is a B is a subset of C, but as you put it so well, C won't be a subset of B, right? There'll be something in C, right? B is a subset of C, but C is not a subset of B because, and you'll tell me what element is in C, that's not in B. And then 3, A intersects C has at least one element. So you'll show me, what actually is in A intersects C to verify, that it has at least one element, right?
Mhm.
And then finally, 4, A cross B equals, and then you'll write the ordered pairs. There have to be 12 of them. Does that make sense?
Yeah, so
I'm just drawing the meta symbol.
basically, um, A, so you're gonna find, I'm gonna find, um, like sets of A, what A equals, B equals, and C equals to verify each and every property in for,
Yeah. And you know what I'll do? I'll just disappear these because the universe isn't letters, is it? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
okay.
So the elements you put here and here,
Mhm.
should be should be these. And that way you can fill in your start to fill in your Venn diagram with these elements, uh, and try to make sure all these properties hold.
Okay.
Yeah, it's just supposed to be a puzzle.
Mhm.
Do you feel more comfortable with that now?
Yeah.
Good.
I do have I do have another question,
That's
and this
fine.
is for number two.
Okay. You want to,
The problem is considered an arithmetic sequence d sub k whose formula is given below. Um, d sub n equals 5 plus 4n for n is greater to 0, which um I've already done that. However, I'm kind of confused on 2b. D sub k equals 5 plus 4n.
oh, did I say 4n? Is it d sub
Sorry,
n?
sorry. I keep mixing up um
Hey,
2A and 2B.
so what did the formula say? It should be,
So for hold on. We're looking at A, or I think we're looking at
I'm
A or
just looking at the formula. Is it d sub n equals 5 plus 4n?
yes.
Okay, because these have to match. The indexing variable needs to match what's changing in the formula as n grows, okay?
Okay.
And A was just defined like what? D sub 0,
So
D
z-
sub
1,
1.
D sub 2, and D sub 3.
Okay, and I'm sure you could do that. Okay. So B is to verify, or what does it say? What's the precise wording?
Prove that this sequence satisfy
Okay. All right, I'll just say D sub K satisfies this recurrence relation. What for n, was it for K greater than or equal to 1?
K greater than or equal to 1, yes.
And I think I said that twice. I think I
No,
said K greater than or equal to 1 twice. It's D sub K equals,
D's of K minus 1 plus 4.
and again, it's for K greater than or equal to 1. I know I said this twice just to emphasize that that's kind of important.
Yeah.
Now, I'm going to refer you to class notes
Okay.
because we did one just almost like this, except for geometric sequence. And I'm going to bring those up because we definitely did this for a geometric sequence, okay? So, I mean, all of the bits and pieces that you kind of need in order, it'll be a different equation because this is an arithmetic sequence, not a geometric sequence. And you also have a WebAssign. from 5-1. No, this is 5-6. Holy cow, this must be day 22. I mean 21, because this is from section 5-6.
No, this is day 20.
Oh, is it day 20?
Yeah.
We haven't had day 21 yet?
Day 21 would be 6-1. And I'm assuming that
Oh, you're right. It was day
because I
20.
saw the day 21 notes.
Is it
Sorry,
in
the day 21 video.
is it in day 21? I'm gonna
Day 21 is talking about big unions and intersections, disjoints,
Oh, yeah, you're right. You're right.
and
It's day
partitions.
20. It's day 20 because
Yes,
it's section 5.6. You're absolutely right. So
yes.
I'm going to bring those up and share my screen with you to show you exactly those. All right, example 4. It's example 4. Because there was a geometric sequence, I gave you the formula. Okay, I said B sub k instead of B sub n, but it's the same idea.
Hmm.
Show that that sequence satisfies this recurrence relation for k greater than or equal to 1. And since it's geometric, the recurrence relation is that B sub k is the common ratio, whatever that is, it's 3, times the prior term. So this was the way the solution went. For k greater than or equal to 1, the given formula, I'm talking about the hypothesis, it's given
Hmm.
right here, okay, tells us that b sub k is 3 to the k, but it also tells us that b sub k minus 1 is 3 to the k minus 1, because this formula works for k greater than or equal to 0. And if we know that k is greater than or equal to 1, then k minus 1 is definitely greater than or equal to 0. So that formula applies, you see.
Okay.
That's why that range for that indexing variable is so important.
Okay.
So we have these two pieces that are true.
Okay. Um, Now, does this formula, the recurrence relation, apply for arithmetic sequences as well?
Uh-huh. Not exactly this formula,
Okay.
okay? But I mean a formula. And this relation, this recurrence relation works for geometric. See how we have to multiply because in a geometric sequence, the way we get to the next term is we multiply the prior term by the R, the common ratio. So the recurrence relation looks a little different, okay? But in an arithmetic sequence, what we have in our hand is the formula for an arithmetic sequence. So this is what's given.
Okay.
And the recurrence relation isn't about multiplying the prior term times a common ratio. It's about adding the common difference to the prior term. Okay. So
And for the prior term,
that's the
um,
b sub k minus 1.
Okay. So if we're using the prior term, don't we like
You can use this formula.
oh, you use this formula and then for d sub n you substitute for d sub k, the value of d sub n and plug into d sub k, right?
Right. When n is k, you would plug in this, but use k. And when n is k minus 1, the formula still works. You plug in k minus 1. And don't
Oh,
forget,
okay.
since k minus 1 is a binomial, you have to multiply 4 times the quantity k minus 1, okay, when n is k minus 1. And that 4 has to get distributed across the k and across the minus 1, okay?
So it's for each term of k for k greater than or equal to 1.
And that works out that you can use this formula for both of these.
Okay. All right.
And so you'll be able to work on the left-hand side, figure out what it looks like, and then separately, remember we can't set them equal to each other. That's a big no-no, but you can work on the right-hand side, figure out what the formula says it looks like, you know, plus 4, and then reduce it and make sure the left-hand side and the right-hand side look like the same thing after you've simplified them both.
Okay. So d sub k minus 1 is the left-hand side for d sub n.
Mm-hmm.
And the right-hand side for, I'm sorry, for d sub n is uh the right-hand side for d sub k.
All right, do them one at a time,
Okay, I'll just do one at a time.
right? You just want to do them one at a time. D sub k is equal to something. And then, so the left-hand side will look like, D sub k, n is k. You can easily figure that out. And the right-hand side of the recurrence relation, right, that we're trying to
Yeah.
prove, which is what's that's our wish, is to prove that recurrence relation. And the right-hand side of the recurrence relation. Sometimes I find just organizing myself really helps me, like figure it out because mathematics is all about just symbols and the order that they're written and what does it mean to have these symbols written in this particular order. See what I mean? That's why organization is so important in mathematics. Isn't that the right-hand side of the recurrence relation? You're digesting what I just said, aren't you?
Yeah, I'm actually digesting.
It matters. Organization is everything in mathematics.
Mhm.
And then you can figure out what it looks like, and these two should turn out to look like the same. And then you can say the left-hand side equals the right-hand side, so the recurrence relation holds.
Okay. So the left-hand side is
You don't need to tell me, okay? I know you can figure it out.
I think I'll just replay the video.
Proof, right? First, you know, notice that d sub k equals something, and d sub k minus 1 equals something by the formula,
Yes.
right?
Mhm.
And once you have that expression for d sub k, and you have that expression for d sub k minus 1, you can plug in for d sub k here, and here you can plug in for d sub k minus 1, and then don't forget to add the 4.
Okay.
And they should turn out to equal the same thing.
All right.
Anything else?
Let me check. Okay, okay. Uh, Oh, and number four, so consider the set A of A, B, C, D, E, F, G, H.
Really?
Yeah,
I gave you a set with letters.
yeah.
What did I do with it?
You just asked me to determine whether the collection is a partition of A.
Oh, yeah. So you have to know the definition of partition. Let's review the definition of a partition. Given a set A, a collection of subsets of A. So the collection, could be A1, A2. I think all of these had three, right? So it just ended A3.
No, no, no. It can be ace of N, actually. I just checked the. I'm just also looking at the notes.
Is a partition of A if three things happen. What's the first thing that your notes say?
Ace of I is not an empty set.
So you don't want any of those subsets to be empty. Good. Two,
Ace of I intersects ace of J, both not being an empty set.
no, their intersection is the empty set.
Okay, okay. So be nothing should be okay, okay, okay. I kind of read that wrong. Ace of I intersect ace of J doesn't um doesn't have anything in common.
Exactly.
Okay. Um and three, the union of the sets is A for yeah, ace of I. Sorry. No, 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 no. Hold on. Ace of I equals A.
The union from I equals 1 to n. You always read the union first. The union
Mhm.
of I equals 1 to n. It's weird because we don't usually read from bottom to top, but we always want to read the lower limit first. So we say the union of I equals 1 to n, or the union from I equals 1 to n. You can say it either way. The union of or union from I equals 1 to n of A sub I is equal to A.
So, meaning the element, we have set A though. So, element of A appears once and only once is some subset ace of I. So meaning ace of so meaning ace of I is a subset of A if it only appears one if the element only appears once. Did I
The
get that right?
collection is a partition. C is a partition of A means this. Each element of A I'm talking about the little elements of A,
Okay.
appears once and only once, in other words, exactly once, in some subset A sub I, and none of the A sub I are. Basically, you're checking to make sure each element of A appears in this union, but you don't want any element of A to appear in two of these sets, because then you would have two of these sets not be disjoint.
Okay. So, for example, we have a set 1, 2, and then another set 2 of 3.
And that would not work out as subsets for a partition of A equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because you can't have two appear in two different subsets in the collection.
So the only thing it would work is 1, 2, and 3 and 4.
If A had four elements, that's good. Let's look at that. Let's say A has four elements, 1, 2, 3, 4. There are a bunch of different possible partitions. There are a bunch. Let's call them P1. P1, you could put each element in its own singleton set by itself. And then you know that none of those subsets of A that we're building in P1 are empty. None of these are empty. Their union is A because each element of A appears once and exactly once and in one of these subsets, and none of these subsets shares any common elements. But what you said would also work. You could put 1 and 2 together, and you could put 3 and 4 together. That would also work. Or you could put 1 and 3 together, and 2 and 4 together. That would work as a partition.
Okay.
Or you could put 1, 2, and 3 together in a subset, and 4.
But 1, 2, and 2, 3, 4 would not work.
That's exactly right, because you would have 2 and 3 appearing in two different subsets, and that would break number 2.
Okay.
And I think in the wording of the question number 4, I asked you to specifically say which part of the definition of partition gets broken if a particular collection that you're examining turns out not to be a partitioning collection,
Okay.
right? Didn't I ask you to identify which part of the definition of partition gets violated?
Mhm.
You read that question really carefully.
Yeah.
Gonna pause the recording for the moment.